Thank you. Thank you for having me, and thank you for the introduction. Just going to see this. So today I'm going to be introducing you to Cactus. Cactus is a computational urban design tool that allows us to coordinate carbon reduction targets with the design objectives of architecture and planning. As the introduction mentioned, this was developed as part of my graduate thesis at Waterloo. And since graduating, I'm continuing to develop the tool with some colleagues. And our intention is to develop this as a broader project trying to model a really comprehensive look at the carbon dynamics of cities. So keep that in mind as I go through, that I'm going to be presenting one module of a broader project that is in progress. And I'm going to be breaking it down to 4 sections. I'm going to go through an introduction, I'll survey the state of the art and the background, we'll look through the methodology, and finally I'll synthesize these concepts in a case study. In the context of Western liberal democracies, we tend to democratize the agency of design through a participatory urban model. And this is great because we're capable of leveraging the local expertise of citizens to create high-quality, responsive urban fabric. However, the participatory urban models has certain constraints. One of which is that they lack specialist or expert information to make qualified decisions. So good urban design hinges on good decision-making, which hinges on good information. And so that's what Cactus is within this process. It's a way for us to provide high-quality information to the stakeholders in the urban design process so that they can make high-quality decisions. The issue with low-carbon, high-density urban fabric, however, is that even for specialists, it's a very complex topic. It's a new topic, and that's partly because the computational resources to model urban energy performance has really been developing for the last couple of years. So this is a diagram by Carlo Ratti. He isolated just the building energy loads, which is what I'll be presenting today, in the city, and isolated the 5 categories that the building energy load depended on. Now, in terms of urban design, those first 3 are the ones we're going to be looking at. And specifically, I like to abstract 3 key energy dynamics. First, we have the way the local geometry impacts solar radiation on the building through the obstruction, reflectance, and conductive exchange of that solar radiation. Secondly, we have that solar radiation actually transmitting through the building envelope, either through the transmittance of illuminants or the conductance of solar irradiation. And finally, we have that solar radiation then contributes to the balance of the building energy load based on the intrinsic thermodynamic efficiency of the building geometries. So with that, we can begin to see what the relationship between urban design and building shape is. And as this diagram illustrates, it has a lot to do with solar irradiation. Specifically, it's the solar radiation and the building geometry. So I'm going to cover some of the state-of-the-art in urban energy performance. What I'll be presenting to you today is the solar radiation module of Cactus. So we're going to be looking at the interaction between passive energy potential through solar radiation and building geometry. And what these studies demonstrate is that there is a significant energy reduction potential due to the exploration of form, and despite this, it's quite often a very ignored variable in urban design efforts. So this study here was looking at 20 different urban fabrics across Europe, and what they did in all the studies I'm going to be showing you, is they kept the non-geometric parameters constant and simply looked at the geometric effect of energy. And in this case, they found there was a 600% variation in thermal energy loads due to the form alone. In this study, we have 6 different urban typologies in Copenhagen. They found an energy variation of 16% and a daylighting variation of 65%. And that daylighting variation And I should add that the energy variation does not scale linearly with density. We can modulate the energy performance based on the geometry. And finally, here we have a study of Toulouse, London, and Berlin. And what they established was a energy performance variation of 10%. And so the reason why we're getting different energy variances here is that each of these research groups are looking at different climatic context and different U values. They have different energy standards which determine the building envelope performance. But what we can say is that there's two takeaways from this research. Number one, there is an energy reduction difference because of urban geometry. And number two, state-of-the-art research teams are engaging in this research, and they're using computational methods and tools to engage it. However, we have not yet seen the trickle down of this urban energy software into mainstream design practices. And this diagram illustrates partially the reason why that may be, and that's because state-of-the-art urban modeling software and state-of-the-art urban energy software tends to be separate. And so it's difficult for architects and urban designers to integrate those two and evaluate the interaction between them. And so that's what Cactus is. Cactus is a way for us to synthesize urban modeling and urban energy performance. And this is the Cactus method. Essentially, Cactus is an optimization algorithm. It consists of three components. You have a form generative component in which we derive building typologies. We then have a simulation engine from which we derive luminance and irradiation metrics in this particular module, although we are working towards also embedding transit and the accommodation of pedestrian comfort. And then thirdly, this is then looped around an optimization loop in order to identify the best performing metrics. Best here being defined as something that the designer or the urban stakeholders determine. So I'm going to begin by breaking down the form generative method. This was my contribution to this domain. I created what we would call an energy-centric shape grammar. Shape grammars are an algorithmic method to create a building typology, essentially allowing us to embed rules for design decision-making into the geometry so that the designer doesn't have to manually input design decisions. And here's the energy-centric shape grammar for Cactus. What you can see here is that the hierarchy of urban generation from the fabric to the building typology to the building envelope is integrated within a density and an energy performance simulation. So by embedding these, by automating these design decisions, we allow us the opportunity to create hundreds, if not thousands, of different development scenarios. So in a coming slide, I'll be showing you 300 possible design scenarios. Here's a close-up of two. What you can see here is the objectives here was to create 7,000 residential units within 15 hectares. And what the algorithm does is create architecturally correct typologies. So this is a video of an earlier proof of concept. This is what I showed for my thesis. The current version is slightly more refined. I'll be showing you that. But what you can see here is that the algorithm, based on a simulated density increase, chooses correctly the typology to produce without the intervention of the designer. So before I begin talking about the simulation, I'd like to talk about some of the underlying assumptions I made for the energy model of Cactus. This diagram here shows you the most important energy trend in the last 30 years for building energy performance, and that is the radical increase of performance in the building envelope. Specifically, what you're seeing is the reduction of the heat transfer coefficient in insulation standards. And what this has done is, previously, the bulk of the building energy loads has been space conditioning, heating and cooling. And while it is still quite large, it has become less significant, and it also less opportunity to mitigate space conditioning through geometric methods. And so what we focus on in Cactus is actually passive ventilation and daylighting efforts. And then secondarily, we look at heat gain. There's a couple of things more I could talk about here about the sort of intricacies of the energy model. But I should add that keep in mind, this then gets embedded within a broader idea of transit energy and pedestrian comfort. Here's essentially the simulation shape grammar. So I showed you the derivation of the building typologies. And so in order to get energy performance metrics, what we do is we take those building geometries and we recursively subdivide the building surfaces to get building envelope geometries, the walls, the windows, and then we encode the U value, the reflectance value, and transmittance value so we can actually intersect it with solar radiation and understand the impact on the interior of the building. And this here is the other significant simulation component, which is solar zoning tools. Essentially what they do is they precisely calibrate the terracing of the building in order to allow a specific amount of solar access to the buildings. And so this is kind of a key thing, a distinction between optimizing for single buildings and optimizing for groups of buildings, is that you start to get into we start to compound into more difficult geometric variations in which you have to trade off the various energy performance of different buildings. So here are the two simulation methods together. This was the geometry I showed you earlier, but now we can see it in terms of passive illumination and passive heating. Specifically, what I've done is I've set a threshold for 300 lux illumination for lighting and 280 kilowatt per 216 kilowatt hours per meter square per year. And if the geometry meets those thresholds, then we can replace that component with passive energy. And so here's that same shape grammar derivation, but now we can see it in terms of the solar irradiation metrics. And you can see quite clearly that there is a huge difference in the interaction between different geometries and its passive energy zones to non-passive energy zones. And so now I will synthesize these the workflow into a case study. It is in southern England in a town called Lewisham. Lewisham is currently undergoing a significant redevelopment as the transit node north of the site is developing into a major interchange. And the typologies are transitioning from the terraced housing fabric towards mid-rise and high-rise buildings, as you can see in these images. And this is the 300 different development scenarios that are created by Cactus. As I said, there were 300 that we looked at, and you can see to the top the corresponding energy performance metrics. And in conclusion, this is a video of the most current version of Cactus. We can see the shape grammar making decisions about what the most efficient typology is, always fulfilling the constraints, which are 7,000 residential units on 15 hectares. You can see it's balancing between mid-rise and high-rise buildings and detached housing. And with that, we understand how we can start to coordinate the carbon reduction targets with architectural and planning objectives, and then hopefully eventually begin to embed this within broader metrics and begin to finally try to communicate and optimize the complex carbon dynamics of the city. Thank you.